I'm very pleased to introduce our presenter, Winston Li. He's a researcher, a part-time academic, and founder of Arima, a company that develops synthetic data for consumer and marketing analytics. So please join me in welcoming Winston. And Winston, I'll turn it over to you.
So let's get started. Today, we'll be talking about synthetic data, and we'll be looking at it from 3 angles. We'll look at what synthetic data is, what's so useful about it, and the different types of synthetic data. Synthetic data is a really broad term, which encompasses a lot of things. So we'll be looking at different kinds of synthetic data and how they're being used. Second, we'll look at a specific application, a specific technology called data downscaling. This is one of the many ways of generating synthetic data. We'll look at what that is, why do we need that, and how the algorithms work. And finally, we'll look at some use cases and how does this benefit a business and why might a business want to use this. As always, if you have any questions, feel free to jump in at any time. It'd be good to have a discussion, so you don't have to wait until the end. Just if you want to throw something in the chat, or if you want to raise your hand, or if you want to just say something, feel free to do that. All right, let's get started. So we'll look at what is synthetic data. Synthetic data is simply data or information that's artificially created rather than generated by real-world events. So if you ever familiar with terms like computer simulations or random sampling of data sets, those are synthetic data. Basically, you write some computer program, you write some code, and you use that to generate some outputs, and that's your data. That's your synthetic data. It's not generated by real-world events, but it's supposed to mimic real-world events. So in other words, it's supposed to look like real-world events, whatever those events might be that you're interested in modeling. Synthetic data can be really anything. You could have synthetic images. So think of Midjourney as an example. You train the machine, you train the AI with a bunch of pictures, and then you are asking it to generate some more pictures. Pictures that are never created, were never created by people, but computer generated that look like what would have been created by people. They could also be text, like ChatGPT. They could be music. They could be videos. It could be really anything. And of course, they could be tabular data. And our focus today will be looking at tabular data because for the most part, for most businesses, they are still using 90%, I'd say 95% of their data that they use are still in the form of tabular data. Things like images and videos are nice, but most businesses don't actually use that, or their use of that is very minimal. And synthetic data enables you to do a lot of cool mathematical simulations or analysis that are not possible before. And we'll take a look at examples of that, and we'll talk about why sometimes you actually need synthetic data to help you conduct certain analyses. The idea of synthetic data is nothing new. It existed way back in the 80s, even in the bio space. If any of you come from a biology background, you might have heard of terms like in vivo, in vitro, in situ, and in silico. In vivo meaning you run some experiment on a live agent like a mouse or a rabbit or something like that. In vitro means you do the experiment in test tubes. In situ means you do it in a real live environment, like you take a little bit of, you have a little bit of a land and you do an in-field experiment. And finally, in silico means in the computer or as a computer simulation. So a lot of what we're talking about today, i.e. using synthetic data to calculate to conduct certain agent-based models, to perform certain experiments, they are like the equivalent of the in silico analysis from a bio standpoint. Why do we need synthetic data? There are 3 common motivations for why we use synthetic data. The first one is replication. In this case, we want the AI to be able to generate objects that are similar to what humans can do, but at a lower cost. So think of ChatGPT as such an example. We ask the computer a question, we ask the AI a question, and we expect an answer. Yes, most of the time, you can also get a professional to answer that question for you. For example, if you have a law question, you ask ChatGPT, or you ask a language model to answer it for you. Sure, you can hire a lawyer, the lawyer can do the same thing, but the computer can do it faster and cheaper. So we want the computer to be able to replicate what a human can do, but at a lower cost. The second motivation is interpolation. This is when we want the AI to fill in the blanks. In other words, something that can be partially done by a human, but it's not as good, and we want the AI to make it better. So in this case, this could be an image generation application where you draw a simple sketch and you want the AI to fill in all the details, all the colors, and make it nicer looking for you. So that could be an example of where you want the AI to interpolate, to generate a synthetic data, to generate a synthetic picture based on your inputs. Or sometimes this is used a lot in market research, which is the space that I deal with, where you have a little bit of a sample. You sample a few people across the country, and you want the AI to help you interpolate, to model out your sample so that you can now work with the data set with a much bigger sample size. And finally, there's also a privacy aspect to it. Sometimes we want the AI to generate data objects that are similar, but also different, to preserve privacy. For example, if you're dealing with people's financial records, or if you're dealing with people's healthcare data sets, a lot of times you want the AI, you want the data scientists to want to work with that data. They want to build models, they want to extract information out of it. But your legal team will tell you can't touch this data set because it has sensitive information. Our privacy law says don't use it. Well, in this case, synthetic data is actually a very good way to compromise for the two sides to compromise. You can have a synthetic version of your original data set so that it's not the same, but it's also similar, so that the data guys can work on their analysis, can build their models using the synthetic data, achieve similar kinds of statistical power, and at the same time, they don't have to violate anybody's privacy. They're not using anybody's data because it's already a synthetic version and the original data set is not preserved, is not being used. So those are some reasons why people may want to use synthetic data. And this is also some of the reasons why synthetic data is getting more popularity in the industry, because people find it as a cheaper, easier to use, and safer alternative to working with real data sets. I have a slide here on some of the quotes on how people think about synthetic data. This result comes from a survey by KDnuggets, where they asked data scientists, what do you think about data? What do you think about synthetic data? And what your plans on adopting synthetic data are. So here are some quotes, and I'll share the slides with everybody afterwards. If you're interested in looking at this, you can. 72, for example, some of the ones that I found really interesting are 72% of people plan to adopt synthetic data within the next few years, with 40% within the next 3 months, and almost half of them say data augmentation is their main use cases. We'll actually be looking at a number of use cases later on where data augmentation is a very key use of synthetic data. And there's a couple of other ones that are interesting as well, mainly being people don't have access to enough data or privacy challenges, and those are the main motivations why they choose to use synthetic data. And finally, to conclude this section, I've left a quote. This is by Anne Cavoukian. She is the former privacy commissioner of Ontario. So she works with the government she's a lawyer by training, I believe. She's works with the government on dealing with different laws and regulations around privacy data and synthetic data, sorry. And this quote here says, synthetic data doesn't present any of the risks associated with the real data, which have the personal identifiers linked to it. in my view, it is going to be the future in terms of privacy and data utility. So one of the things we'll be looking at throughout the rest of the presentation is the balance between data utility and privacy. How can we preserve privacy while at the same time increasing data utility? And that's a central theme in synthetic data. All right. Happy to pause here for a second to take any questions if you have any. Otherwise, we'll head over to the next section. Okay, the problem of data downscaling. So one thing I want to stress is that generating synthetic data is a sort of a broad term for many tasks that are very different. For example, if we are talking about generating synthetic text data, this is a very different technology than generating synthetic images or generating synthetic music or generating videos. These are all, even though they're all synthetic data, they're actually very different tasks. And so a lot of people devote their time on researching methods to generate one type of synthetic data. Here at Arima, one of the things we do is generate synthetic tabular data, and in particular, synthetic tabular data used for marketing and consumer analytics purposes. The specific problem we study is called data downscaling. And in this next section, I'll spend a little bit of time talking about synthetic data downscaling, what problems does that solve, and the end product, which is called the synthetic population. So synthetic population is a data product that we build and we commercialize as a result of data downscaling. So let's look at the problem of consumer data. By consumer data, I mean data about people like you and I. You and I are consumers, and therefore everything we do is consumer data. Consumer data has a really wide range it includes almost everything about you and I. It includes our demographics, like who we are, where we live, what kind of our ethnicity, our language, income, our family. It also includes our financial patterns, like where do we bank with, our credit scores, how many credit cards do we have, our shopping behaviors, media consumption, what our psychographics, beliefs. All of these things are part of consumer data. And in this particular presentation, we'll look at how synthetic data is applied to consumer analytics, and in particular, how can we generate synthetic versions of consumer data. The main challenges in consumer data there are two things. One, difficulty in data collection, and two, privacy restrictions. Difficulty in data collection. A lot of consumer data today is collected through surveys. You can see there are companies out there like Nielsen, like Ipsos. They specialize in collecting surveys. So their jobs is actually to sample data from the population. It's very costly to sample people. Very often you have to give them money. Very often you need to select who it is that you want to sample. You need to keep their contact information. You need to know everything about them so that your selection, your panel is representative of the country. And you also need to have people to come up with the questions, to actually conduct these surveys, and to organize, clean data. So this whole process is very costly, which means that the amount of information you have is often very limited. And the second challenge is privacy. When you sample things about people, that's their personal information, and they don't want you to release that information in public. People don't want you to tell them so-and-so makes X amount of dollars every year. This is the car they drive. This is what they think. This is the political party they will vote for. All these things are considered highly sensitive, and nobody wants you to tell that to the public. So how do we So how do we deal with that? Well, synthetic data is a perfect candidate to address these problems. Here, we'll look at how Arima tackles this problem by building a synthetic population using the sync algorithm. The sync algorithm is something that I've developed and published back in 2018 or 2019. And here I want to walk you through a simpler form of the algorithm so that you can get a taste of it. You can get a taste for what building synthetic data is actually like, why synthetic data is a very accurate representation of actual data, and what benefits it can bring to businesses and researchers. Okay, consumer data often comes in one of two formats, what we call respondent level and aggregated level. In the top view here, this is what we call respondent level data. You would typically have this data set from a survey or from your own consumer profiles, for example. It's called respondent level because every respondent or every person is one record. So here you can see this first person, he or she has an ID. We know where they live, so they have a postal code. We know their age range. We know they have a bunch of things, a bunch of questions they've answered, like, do you own a dog? Yes. Do you own an SUV? No. Do you shop at Walmart? Yes. Do you watch the CNN? Do you watch CNN? Yes. And the second person, let's say this is a she, she lives in a different area and has a different age and has responded differently to these questions. This is respondent level data. Alternatively, you also have something called aggregated level, and this is the bottom data set, where rather than having every record for each person, you now aggregate people to the postal codes. So for example, now here we say in this postal code, we have 53 people, 12.3 of them are between the age 30 to 34, 18.5 are between the ages of 55 to 59, 48% own dogs, etc., etc. And obviously the second postal code, it's got a different population and a different distribution, of these variables. So when dealing with consumer data, these are almost every data set come in one of these two formats. There are some problems with both of these data sets. The first one is, so let's look at the respondent level data first. This is the one where you have one record per individual. The problem with working with respondent level data is that although it includes a lot of details about every individual, so you would know this person, you would know a lot of things about them, it often has big privacy risks. One of the things you might say is, well, this doesn't even have a name, it doesn't have an email, we can all wipe that out. What kind of privacy risks does it have? Sometimes in Canada, postal codes are very small. Your postal code, in Canada, we have just over 800,000 postal codes. The average postal code has about 47 people. But if you go to some smaller areas, you can have a postal code with under 10 people. So if you had that information, if this is a really small postal code and there could be only one person who's between 30 and 34, and you can actually go to that postal code and identify this person. Or if in this postal code, there's only one person with dogs, you can go in there, you can see which person has a dog, and you would then automatically know they own an SUV. They don't own an SUV and they shop at Walmart and they, everything else about them. So the process of data anonymization, that is to get rid of personal information, sometimes doesn't prevent you from identifying people. And the whole central theme around privacy in consumer data is whether you're able to re-identify that person. And if you have a chance of re-identifying that person, then this data set has privacy risks. So very often, individual level data has that kind of problem. And the other challenge is sample size. The way you would get a data set like this is either through panels meaning market research. So you call up some market research companies and you say, can you go and ask people these 4 questions? Do you own dogs? Do you have an SUV? Do you shop at Walmart? And do you watch the CNN? And the market research company that you work with would charge you a fee, and they would go and they would call up their customers, call up their their panelists, and they would ask them that question. And as you can imagine, they can only call a very small percentage of the population. If you pay attention to elections, typically in Canada, when it's election time, people will conduct surveys and polls and ask, which party will you vote for? The sample size for those are usually about 1,000 people. So they can only afford to call 1,000 people to get information from this because they don't have a bigger budget than that. And this is a costly process. Versus in Canada, we have 40 million people. So out of the 40 million people, they have to carefully select 1,000 to be representative. The other source that this information could come from is company CRMs. So basically companies' internal databases. And you can imagine that if unless you're a very big business like a Loblaws or a Royal Bank, chances are you might have only a couple thousand or maybe 10,000, 20,000 customers, and this information you have is again very limited. Then we're dealing with aggregated data. Aggregated data sets basically turn people data into geography data. In other words, you're taking people in an area and you're averaging them. So by doing so, you no longer have data about people, and instead you have data about an area. So here you can see, rather than knowing individuals, we now know in this postal code, A1A1A1, there are 53 people, and this is their distributions. So I don't know what the 53 people look like. I only know 12.5% of them are between this age range, and about half of them own dogs, and just over a quarter of them have SUVs. Now, data sets in this format it's much safer because you don't have individual information anymore. But on the downside, you also lost a lot of information. For example, if I asked you, of the 12% of the population that are 20 to 24, how are they different? What do they look like? Are they kind of similar, or are they very different? You don't know that. Or if I ask you, we know half of the neighborhood own dogs, and about 3/4 of them watch CNN. Are they the same people, or are they different people? Are dog owners more likely to watch CNN, or are they less likely to watch CNN? Or maybe the two events are independent, and being a dog owner actually has no influence whatsoever on whether you watch CNN. And as you can see, being able to answer such questions is really important, because if I know dog owners are more likely to watch CNN, maybe if I'm a pet food or a pet vet or a company like that, I might want to advertise on CNN. Whereas if I know that dog owners tend to stay away from the CNN, I may not want to advertise here, or I might want to find some other channels of reaching them. So knowing that information is all very important. You can't get that information from individual level data if you just compare the two columns. But if you have this aggregated view, you lost all of that information. So we looked at two different data sets. We now know their pluses and minuses. In the ideal scenario, we want a national level data with both granularity, in other words, individual level, and representation, and it uses no PII. PII stands for personally identifiable information. So in other words, it has no way for you to identify back to the person. This is the ideal scenario, but however, we don't have that. So instead, we use a synthetic population. A synthetic population is a statistical reconstruction of the true population. Remember, in this case, the true population is unknown because we cannot sample everybody in the country. We model that. We model that when using input data sources that are less granular. So we have less granular data sources like the aggregated view, because this one is safer and is usually more comprehensive. By the way, if you ever looked at the Canadian census, the census is in this format. So the census is one of the best information for people best sources for people to make information, to make conclusions about the population. And this is the format that the census is in addition to a lot of other commercially available data sets that people could purchase. So
can I just chime in for 2 seconds?
Yeah, please.
So as a sort of just a ploy, we have StatsCan coming in on November 2nd for a presentation. So they'll be talking about census data. So thank you for giving that beautiful segue.
Great. Right. So the problem, the ideal solution is if we can take aggregated information like the census and reconstruct individuals from that so that we can gain both the best of the two worlds. We have both granularity and we also have full national representation. And that's what a synthetic data does. So that's what the synthetic population does. And of course, synthetic population is a form of synthetic data. Yeah. Oh, someone has a question. Can you clear what PII means? PII means personally identifiable information, which includes basically anything that you can identify a person with. So your emails, your phone numbers, your address, your social insurance number, your address, your identity of any kind, these are considered PII, or personally identifiable information. Okay, great. The synthetic population does not depend on the availability of PII for matching. This is a really important key. A lot of technologies today out there, they do some form of matching. For example, they'll buy different data sets from different places and they'll try to match your email, or they'll try to match your address or match your phone number and build your information that way. The synthetic population does not do that. The synthetic population is purely mathematically generated. It does not require you to put in PII up front, and it does not come out with PII. So that entire process is quite safe from a data privacy standpoint. Okay, here's the picture. I'm not sure how many of you game. I don't, but I do know there's a game called SimCity, and I think the synthetic population is a very good version, very good example of that. If you played SimCity, you know it's a game where people build cities, and this is probably an older version of a picture I found, but this is what it looks like if you were to build a SimCity. You can see it's clearly not a city. By looking at this picture, you'll know this is not a real city. But nonetheless, it looks like a city. There's a lot of factors that, mimic a real city. There are city centers or buildings or roads, and the roads make sense. They're not real roads, but real roads do look something like this. And there's stores, and stores probably appear in clusters and malls. So stores are not like all over the place, scattered around the city. There are a residential area, business area, etc. So it's not a true city, but it gives you a lot of information about what a city looks like, and it's a synthetic city. And this is exactly what synthetic data is looking to achieve. It's not real data, but it looks like real data, and you can still get useful information out of it for whatever analysis you're doing. Okay. Let's take a look at how people build a synthetic population. This is the sync algorithm. This is a simple version of the sync algorithm, which I've developed. And I want to take you through an example of how this process works so that you understand a little bit about what we do, but also you get a sense of how a particular synthetic data generation algorithm could work and what's the logic behind synthetic data. So let's say we have a very, very simple neighborhood, a simple postal code of just 3 people, size being 3. We know one of them is 20 to 29. We know one of them is 30 to 39, and one of them is 60 to 64. Why are these things in 5-year increments? Well, that's actually how StatsCan report their data. And since StatCan is coming, next, I want to kind of say a little bit of something about them. StatCan is the most important source of information, of consumer information for this country. The census they do every 5 years. It's not perfect, but this is the single source that everybody uses. Everything that you see in consumer analytics for this country, whether it's us, whether it's medical research, urban planning, whatever, the census is the ultimate go-to for a lot of that information. And so it has very, very profound influence on how consumer analytics is developed in this country. So do pay a lot of respect to them. Age buckets, this is how stats can classify their age ranges, and this is how almost everybody in this country classify age buckets. The three individuals come from three different professions: construction, IT, and healthcare. And the three of them have, one of them is a high school grad, two of them are university grads, one of them single, two of them are married. This is all we know about this postal code. This neighborhood of three people, we have some aggregated information. So the question now is, can we generate a synthetic population of three individuals based on the aggregated information that we're provided? And this is our task. We're given a real data set. We want to downscale it. Downscale meaning you take the aggregated version and you make it finer, so you downscale it, and you create three synthetic individuals based on this information. So how can we do that? Well, without loss of generality, let's just assume that we give them an ID. So the person who's 25, we'll call them person number 1. The 35 to 39-year-old guy, we'll call them number 2. And the 60 to 64-year-old guy, we'll call them number 3.
I'm calling Mr. Input for me, please.
Sorry? I didn't quite hear the question. I couldn't quite hear you, sorry. Would you maybe type it in the chat?
I think it was just an error, Winston.
Oh, okay. Okay, then no problem. We'll continue. Okay. The way we calculate synthetic data is by looking at these variables in a conditional format, in an iterative way. So I'm sure most of you come from a data background, so you've taken at least a little bit of probability. You know this notation. This is the probability of profession given age. And this, of course, means the probability of education given profession and age, and the probability of marital status given the previous 3. So there are 4 variables that we want to model out for each of the synthetic individuals, and we do that in an iterative format. So we start with the first one, we do the next one, we do the next one, and we do the next one. And each one we add, that depends on the previous ones. So we just started off with giving everyone an age. The age is really nothing more than just randomly assigned. So we rank them from the youngest to the oldest. And now our job is to assign profession given this person's age. To make a prediction, we train a model on aggregated data sets. Remember, working with a source like census, we have aggregated data sets across the country. So in other words, for all of the 800,000 postal codes in Canada, we know what are the age distributions of every postal code, and then we know what are the profession distributions for all of the postal codes. So we can develop a model to learn the patterns of profession given what the age of the neighborhoods look like. For example, probably we'll find, I haven't run this myself, but probably you'll find that there's a very strong correlation between the percent of construction workers and the percent of young people in the neighborhood. We know that construction is typically a job that's all, you need to be relatively young. And so therefore, if you have a postal code with a lot of construction workers, chances are there are also a lot of young people in that postal code. So these are some of the correlations we can extract. Similarly, we know that if you're in healthcare, people in healthcare are typically very well educated. Maybe you're a doctor and you need your MD, or you need your advanced training. So if you were to look at correlations at the postal code level, you probably find that postal codes with an increasing number of healthcare professionals tend to also have people with higher educations. Again, these are just patterns that you'll find from working with postal code level data or with aggregated level data. And it's based on this correlation pattern that we assign values to individuals. So now we come back to our little data frame. our little data set, we have persons 1, 2, and 3. We know that for the first person, they're 20 to 29. So think of them think of people as a one-person postal code, if you will. In this postal code, there's one person, and this postal code has 100% of your population being in the 25 to 29 range. Remember, this postal code is really just one person, so obviously your population size is 1, and your distribution would be 100% for the value of whatever that person is, and 0% for the other values. Similarly, for your second person, again, it's a one-person postal code. 100% of that postal code is 30 to 35 because that's the only guy in that postal code, and every other value is 0. And for the third guy, again, 100%, 60 to 64, everything else 0. Now, when we have this information, we can actually start making a prediction. Remember, we learned the pattern. We learned from working with postal code level data, the relationship between the distribution of age in this postal code and the distribution of profession in that postal code. So now we have 3 postal codes, 3 individual one-person postal codes with their age information. We can make a prediction. We can ask the model, what do you think the profession distribution of a postal code, of a one-person postal code is, if 100% of that postal code is people from 20 to 29, 25 to 29? The model will make its prediction. So the model will say, I think 40% chance this postal code will be construction workers, 35% will be IT, 25 will be healthcare. And for the second postal code, it has a different distribution. And for the third postal code, it has a different prediction. Now, every individual can only have one profession. So the fact that we've made a prediction and it's a distribution is not super helpful, because one person cannot have 3 professions. They can only have one profession. So now that we have this distribution, we want to be able to assign a value for this person based on that distribution. And the way we do it is by looking at your probability, how your probability compared to your other professions. So if you look at the first person, the model has predicted that he's got a 40% chance of being a construction worker, whereas he only has 35% chance of being an IT professional and 25% chance of being a healthcare professional. So for this person, we think he is most likely a construction worker out of the 3 possible professions, given the fact that he's a 25 to 29-year-old. Similarly, we can see of the 3 people in this postal code, this person is also the most likely guy to be a construction worker, with 40% and the other 2 being 34% and 10%. So this person is a clear winner. He is both the most likely person to be a construction worker, and of all 3 professions he has, construction worker is also the most likely profession of the 3. So let's say this is your construction worker. Remember, from our census level data before, we know there's only one construction worker in this neighborhood. So the moment that we assign construction worker to this 20 to 25-year-old, this option is no longer available. And basically the rest of the people have to be IT or healthcare. You cannot have a second construction worker in the area because the census tells us there's only one such person. If you look at the second person, this person, he or she, is 33% chance likely to be an IT professional and 33% chance likely to be a healthcare. They're equal, so we don't know which one to assign, but let's look at the third person. The third person is more likely to be a healthcare professional with 50% chance versus only 40% chance of being an IT professional. So we'll assign healthcare to this person, and for the second person, they don't have anything else to take, so they'll just take the IT. They'll just take IT as a profession. So now, through assigning, we've given everybody a profession based on model predictions and also based on how they compare with their neighbors. So in other words, you have to be more likely to be a profession and also more likely to be your neighbor in order to be assigned that profession. And similarly, we use the same logic. Now, assuming we know people's age and profession, now if we're told by census, If one person is a high school grad and two people are university grads, I'd ask you, who do you think is more likely to be the high school grad? You'd probably say, well, I'm going to go with construction worker, and IT and healthcare seems like they're all more, seems like they require a little bit of an education, so maybe I'll assign them as university. And finally, marital status, again, same thing. We know one person is single and two people are married. Who do you think is a single one? Well, we'd probably say of the three people, based on their age and maybe also based on their profession, I'd say I think the first person has a higher chance of being the single, so we'll assign him that value, and the rest of the two are married. And this is essentially it. That's how you construct a synthetic population based on aggregated sources like the census. A quick summary: a person gets assigned the most likely outcome among all outcomes. The most probable people in a region gets assigned, so you have to be the highest probability of your neighborhood in order to be assigned. The number of assignees match the given regional total, so this information we produced agrees with what the census tells us, namely people's age distributions, people's profession distributions, education, and so on. And obviously, this process does not depend on knowing individual identities. So I didn't really know who the 25-year-old is, who the 35-year-old is. I'm creating this data set purely based on probability. And one last thing I'll say too is this is not a deterministic data set. I'm not trying to say this is 100% the outcome of what that neighborhood will look like. If you go to that neighborhood and you check it out, it could very well be different than what we predicted. This is only one of the many possible predictions and probably the one with the highest, most likely outcome. So if you're ever familiar with statistical terms like maximum likelihood estimator, this is the same kind of idea. This is a maximum likelihood estimation of what the population could look like. We're not saying this is what the population looks like. This is just an estimation. Question. I think the information can still be biased. The construction could be an engineer. Sure, the information could very well be biased. Again, we're not saying this is what the neighborhood looks like. This is just one of the possibilities. That's all. So you could have, depending on your data, maybe when we look at our actual data set, you'll find that being a construction worker don't correlate with age at all. Maybe that could be the case. And if that's the case, you might get a different assignment. So I'm only walking through an example as to how this being one way of how data could be assigned, but this is by no means the only possible way. How would you evaluate data, the quality of synthetic data generated in a systematic way? One of the most difficult challenges in synthetic data is how to evaluate it. And a lot of it still comes down to eyeballing, unfortunately. Even if you think of, generating synthetic images, you ask the computer to generate a picture, and then you ask how good is that picture. There is no real metric today on how you would evaluate the quality of an image. There are, in the space of natural language processing, there's some people have came up with some evaluation metrics, like in terms of you have a language model, it generates some text, and you can evaluate that and say this is good, this is not good. But in general, it's a space that people are actively researching on. Specific to our case, people could as well ask, how do you evaluate the quality of your synthetic population? So for example, people take an aggregated data and we present these 3 pieces of information. How do we know this is accurate versus this is not? Something that I'll get to a little bit in the end, but it's definitely an area where there's no definitive answer today. To continue along the same thought, isn't this how biases are created in AI? Depending on how you view bias, sure, if your input data is biased, then what the model predicts is biased. So if you want to maybe elaborate a little more on what you mean by bias in this case, I'd be happy to sort of talk about that. Does the order of the variables matter? Yes, it does. In our particular methodology, in our particular approach, it does. In most synthetic data generation tasks, actually, the order of inputs will matter, because most of them work in a sort of in a conditional format. Like if you think of language models, you're building it word by word. So how you phrase your question, for example, could matter. In our case, for sure, if you started with a different order, then it matters. It does matter. In the data product we commercialize and we sell, we have about 50,000 variables. So there's a lot of information. There's a lot of different measurements on individuals, and order will for sure matter. It's details that I won't get into this discussion, but there are some ways where you can sort of look at how general a variable is and use that to determine the order. So for example, things like age or income are typically what I consider variables that are very, very general, like they impact a lot of other things, so they should start first. Whereas some variables that are very specific, like do you watch Mississauga News, do you read Mississauga News, and that's a very specific variable, and that will come at the end. Anything else? Okay, thanks. Another quick question. In the example, if you set the first person to construction, does that change the probability the next individual belong to the remaining categories? It doesn't change the probability of them being belonging to the next other categories. Remember, these probabilities are learned from the input data set. So in our case, if we know someone is 30 to 39, a model will learn by looking at the correlation of age and your profession, and that pattern doesn't change. However, what it does change is the number of slots available. So for example, going back to our example here, if we knew there are 2 people in this postal code that are construction, if we know construction had 2 slots rather than 1, then that would change the outcome, because that would then make your second person a construction worker as well, because that being a construction worker is slightly higher than being the other professions. And if there were 2 slots, then that person would get slotted under construction worker. So it's the census level, it's the census data that determine, well, it always comes from the census, but it's the postal code level data that determines how many slots there are in that postal code. And it's the correlations at the postal code level that determines what profession this individual are more likely to be in. Okay. How do we use this? How does this benefit a business? Every first-party data set is a subset of a synthetic national population. Companies will have first-party data sets. These will be users, customers of the company. If you're a bank, you have customers, you have people's information, but of course, you will not have everybody's information. So you have a first-party data set, you know a lot about your own customers, you probably know very little things about your potential customers or people who are not yet your customer. So synthetic data, synthetic population is a good way to augment your existing data. Your existing data is a part of the of the national population. And since we don't have national populations, it's your first party data is a part of the synthetic national population. So remember in our one of the previous slides, we looked at people using synthetic data as a way to augment first party data. Well, you can augment your first party data in two ways. In the first case, consider you are a bank. Let's say you're the Royal Bank, for example. You have 11 million customers. There are 40 million people in the country, which means there are another 28 million, which are not yet your customers, and you would want to know information about them. So you can augment your data set into a larger population. In addition, of the 11 million people who are your customers, you know some things about them, but you probably don't know their life. Your bank knows they know how much you're making, they know what are you spending, they know a lot of things about you. But there are many more things that they don't know. For example, your bank may not know if you have a dog or no. And that's a piece of information found in the synthetic data, and that could be used to enrich the bank's knowledge of existing customers. So you can enrich your data in one of two ways. And here's an example. You've got sort of data granularity on one axis. In the y-axis, obviously, you want to move up. You want to be more granular. But at the same time, the ability to share or use your data is on this other axis. And it's sort of a trade-off. The more granular data you have, the less usable it will be. And if you want to make it usable or shareable, you have to give up on some of that granularity. So synthetic data is kind of an augmentation to that, where you're able to preserve both. And here's an example. Here is a data universe. This is the entire national population, of which you've got your first party data being a data subset. So let's say this is your bank customer. You have your media supplier. For example, if you choose to advertise on Facebook, if you're acquiring customers there, this is Facebook's customers and Facebook's users, and some of them are your current banking customers, some of them are your prospects. This is your category user. So for example, if you're selling credit cards, this might be everybody who needs a credit card. Your competitors' data is there, third-party data, it's somewhere here, and your prospects are all out here. And so the question is, you've got all these bits and pieces, how do you actually connect all of them together? It's very difficult because your bank, you cannot share email addresses or phone numbers or any identities with one of these parties to match. So matching data, connecting dots becomes really difficult. Geography or postal code is not considered personally identifiable. So postal codes are safe to use. And therefore, constructing synthetic data or synthetic population provides a very viable way for businesses to try to connect all of these information together. In fact, in Canada, if you buy or sell data sets, very often they'll come at the postal code level. So they're aggregated to the postal code level, which you can then use to join with your first party data sets. And then you can use technologies like the sync algorithm to produce synthetic populations, which then you can use as an estimate for what the true universe looks like. And lastly, we'll conclude with looking at some use cases. These are all use cases that our customers conduct with working with our synthetic population data set. And this hopefully gives you some examples of how people could leverage synthetic data in their businesses. Retail site selection is one example. As you can see, synthetic data in our synthetic population data, individuals are all typed. Oh, we have a question, so maybe let me take that first. Is it possible to have applications in the clinical space with synthetic data? For sure. In fact, this is where synthetic data came from. We don't play in the clinical space, so my knowledge in that is very limited. But yes, I know it is a very big thing. There's a company in Ottawa. It's called Replica Analytics. It's founded by a U Ottawa professor, I believe, and they look at synthetic data for the clinical space. So this might be something that you're interested in looking at. Okay. Retail site selection. This is a study that we've done with Coke last year, Coca-Cola. We did a presentation on that actually at the Toronto Machine Learning Summit. Basically, Coca-Cola is looking at optimal locations for their vending machines. So they want to know where to place these vending machines. And obviously, they want to be placing machines in areas where they think there are lots of people where, that are potentially buying alcohol, buying beverages, or kids or schools or such. So using data sets like the synthetic population, combining that with their first party data, i.e. how much money they're making per vending machine today, they have developed a model that basically predicts how much money they will be able to make by putting the machine in one area and knowing what the people look like in an area around that. So in the end, I think after the model is done, they ran that model against all their existing vending machines. They have about 30,000 across the country. They took the ones that are not selling. They took the ones that have low revenue, and they picked new locations by running potential areas through their model, and they then moved some of the machines to the better locations. And in the end, you can see they increased average sales by 17% just by moving machines to an optimal location from a model that makes predictions based on historical revenue and population around the area. Okay, so another question. I was wondering if you know any developments in integrating data, synthetic data, to provide real-time information for users. We do that. Actually, in addition to data sets like age or income or gender, which don't change a lot, in our synthetic population data, we also include mobile tracking data. So your mobility, your mobile patterns, so basically where you move throughout the day, and all of these come from your cell phones. So that's a real-time data set. We get feeds on a daily basis. That's part of our synthetic population as well. How we model that is a little more difficult, so I didn't go through that in this presentation, but that's also part of the ingredients. And actually, for this Coke case study, mobility data was a major part of it, because you can imagine there are areas like office buildings or schools where there are no residents beside it, but people do come by during the day, and you still want to be able to make predictions correctly. So yes, that's definitely something. The other thing people have done is to also integrate things like credit card payments, social media data into synthetic population as well. So you can overlay a lot of data sets on it to make it a very rich data set. And a lot of them is real time or near real time. Okay. Another example is market sizing. I don't know how many of you are interested in a consulting life or have worked in consulting in the past. I spent a little bit of time in consulting. I was at PwC for a while before I started Arima. One of the major tasks people ask is market sizing. So they'll ask you to, they'll say, we're a company, we're trying to launch a credit card. How can you give me a size? And this is the people that we're trying to target. Can you give me a size of how big that market is? And from that, we can then figure out, if 10% of our target market gets our credit card, this is how much money we make. This is how much it costs to start this new business unit, and whether we should do this or no. So this is a very common question that a lot of people ask in consulting, and being able to size the market is really, really important. And synthetic data, synthetic population, is a great way for people to quite easily sample the market. So you can see here, I've got some examples. Here's an audience with people who spend money buying lottery ticket. They spend $20 to $29 or $30 or more. So basically, people who spend $20 a month buying lottery ticket. There's about 6 million people in Canada or about 20% of the population do that. So assuming this data is accurate, then of the 60 of the 54 of us on this call, there should be about 10 of you that spend more than $20 a month on lottery tickets. Now, of course, the 54 of us on the screen is not a representative population of the country, so it may or may not agree. But if you look across the country, you should be roughly expecting 1 in 5 Canadians spending 20 or more on average on buying lottery tickets. And here's another audience. We're looking at people who spent, who went to home hardware and who are looking to participate in woodworks, building or finishing their own building projects at home. There's about 183,000 people. So here, if we were to do a consulting project for home hardware, we could tell them, maybe if you're thinking of targeting this group of people, well, this is how big they are, and you can work out your market and your potential revenue from that. Customer insights, obviously, being one of the important things as well. Here's an example. We're looking at people who shopped at Home Depot in the past 12 months. What do they look like? Here's their age distribution. Here's the income. Here's their level of education, and so on. And again, you can get all of that information from the synthetic population. Marketing budget allocation is also something we do, and actually something that we offer to a lot of our clients. If you're trying to reach a particular group of people, I'm trying to target potential credit card buyers. How many of them are in the country? What media channels do they consume? What are the most efficient ways of targeting them? Should I put my money in Facebook? Should I do it on Google? Should I do it, should I do a TV commercial? All of these different options. Which one do I get the best reach and coverage? So if I want everybody to know, everybody in this country to know, I'm Tim Hortons, I'm now rolling out a new credit card. What's the way to get the message out with the minimal budget possible? And geospatial analysis is the last example here. Looking at an area of the country, what do people look like? If I have a target, here, for example, my target is people who's got a mortgage with Bank of Nova Scotia. Where are they? Are they more concentrated? Are they less concentrated? And where are my store locations? Where are my branches? Here's an example of this is a Scotiabank branch. How many people are visiting my branch? What do the customers look like around it? Do I have Scotiabank customers? Are they banking with TD? Are they banking with somebody else? What advertising avenues are there to reach them, and so on. So geospatial analytics is also a big part of what we do, because our synthetic data, the synthetic population data, is attached to postal codes, and postal codes can be plotted on the map, and it can be you can work out distances to store locations, to out-of-home advertising boards, to your competitors' locations, and so on and so forth. So those are some of the applications of a synthetic population in how it could help businesses making decisions. So that's it. This is all of the slides I have. Happy to take more questions if you have any.
This is great. Thank you so much, Winston. Very interesting, and you're doing some great work in this area. So you talked about companies making like operational decisions and sort of reallocating their scarce resources, like maybe Coke with their vending machines. They've got they're trying to maximize revenues. That's kind of cool. But so do you have any like accountants? I'm an accountant, obviously. When we do financial statements, we're always looking at impairments of assets. So we actually, generally what we'll do is we'll try to figure out, we project the cash flows that might come from a particular asset and then discount it. It's quite subjective, but it strikes me that you could use this kind of modeling, like let's say it's a vending machine or a set of vending machines, and you were trying to say, are they impaired in any way? Or, you could use this kind of modeling to sort of project the revenues. I don't know, dude. So that's my question. Is it used in financial reporting at all?
Not at all, because we're a 15 people shop. And when you're only 15 people, you need to be super focused. You can't try to sell to every industry possible. But for sure, I could see lots of applications in that space. So for example, when you're trying to do amortization or something like that, I took many years ago, I was very briefly an RSM student, so I took RSM 220, and then I said no, this is not for me, and then I switched programs. But we do learn things like amortization, and so you do it like linearly or whatnot. If you put in something like mobility data, let's say if it was a sort of an outdoor like a store or something that's outdoor, like even vending machines, for example, you could amortize it by traffic instead of just doing it in a linear way. So there are definitely lots of applications. We don't touch them, but they're there, which at some point, hopefully, when our synthetic population data has more adoption, others could just use the data to do whatever they need.
Yeah, because it's a more refined way of estimating things like fair value or whatever. Again, as accountants, I think we have some sort of heuristics and rules of thumbs that we've used historically, but all of a sudden this is giving some good power, to trying to refine the estimate. So that's incredible.
Competitive analysis is also something that a lot of customers do. So for example, let's again say if you're Scotiabank, you have a branch, that branch is not doing well. You have 3 other branches around you. Maybe one of the things to look at is to use the synthetic data, use synthetic population to figure out who are the users that are going to the other branches. And maybe it's your own problem, your problem. Your branch is not doing well because you're not offering the right support for the right languages or the right products or right financial advisors. Or it could be a geography thing. Maybe in this area, people just don't go to branches anymore, and the BMO branch next door is also doing badly, and then you should just shut it down instead. So looking at being able to estimate how your competitors are doing too could be a big use of this.
And often we use the concept, not to beat a horse here, but in accounting of highest and best use, we measure fair value based on highest and best use. So here you can model what would the highest and best use be. Maybe we're not using our assets currently in the best way. I'm thinking again, those vending machines, right? Just move them, and then they're in a better location. That would give you a higher return. It's fascinating. Do we have any other questions? Anybody else? I mean, we've had some good questions throughout. But I'm mindful of time. So Winston, thank you once again. This has been incredible. Really nice, insightful, view of what you're doing, but also digestible for those of us who are not data scientists. So we thank you very much for that.
Thank you, everybody, and great to be here. And hopefully there's one last thing. Oh, thank you. Great. And hopefully it provides some perspective to you guys on how synthetic data works. And hope to see you someday. Thank you.
Okay, thanks. And everybody, we've put some, our next seminar series item is on October 4th, and it's entitled Housing is the #1 issue in Mississauga, telling the story through data. And we put a link there. So take care, everyone. And thanks again, Winston. Have a good day, everyone.
Okay, bye.
Bye-bye.